Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
1859 Gustav Kirchhoff on the theory of heat radiation. The year 1859 witnessed a confluence of scientific innovation, a moment where the seemingly disparate realms of heat, radiation, and the very nature of matter began to coalesce into a coherent understanding. It was in this context that Gustav Kirchhoff, a name now synonymous with profound contributions of physics, published his seminal work on the theory of heat radiation. This essay will endeavour to illuminate the genesis, substance, impact, and enduring legacy of this pivotal contribution, tracing its roots and ramifications with a rigor commensurate to the subject's significance. Kirchhoff's work did emerge from a vacuum. The intellectual landscape of the mid-19th century was rich, fertile ground for his insights. The concept of heat itself, long understood as a tangible form of energy, was undergoing a rapid transformation. The work of individuals like James Prescott Joule and Rudolf Clausius, among others, had demonstrated the equivalence of heat and work, establishing the first law of thermodynamics. This foundation provided the bedrock upon which Kirchhoff would build. Furthermore, the burgeoning field of spectroscopy, pioneered by the likes of Robert Wilhelm Bunsen, Kirchhoff's colleague and collaborator, played a crucial role. The ability to decompose light into its constituent spectral lines and to identify the chemical elements present within a luminous source was profoundly transformative. Bunsen and Kirchhoff's work had already established the relationship between the emission and absorption spectra of substances, a vital precursor to Kirchhoff's later insights. The essence of Kirchhoff's 1859 paper rests upon a single, elegant principle, now known as Kirchhoff's law of thermal radiation. This law states, very simply, that for an object in thermal equilibrium, the ratio of its emissive power to its absorptivity is a constant, and this constant is a universal function of both the wavelength and the temperature of the object. To clarify, the emissive power represents the radiant energy emitted by an object per unit time and per unit area at a specific wavelength, while the absorptivity signifies the fraction of incident radiation absorbed by the object at that same wavelength. This seemingly subtle assertion, however, held within it profound implications. It implied that the radiation emitted by an object is intimately tied to its ability to absorb radiation at the same frequency. Kirchhoff's proof of this law, provided in his paper, was a masterpiece of logical deduction. He considered a cavity, often referred to as a blackbody cavity, containing objects of varying composition and capable of exchanging heat with each other and the surrounding walls. He then argued, using arguments based on the principles of energy conservation and thermal equilibrium, that the ratio of emittance to absorptance must be the same for all objects at thermal equilibrium. If this were not the case, stated Kirchhoff, then energy could be transferred from objects of lower emittance-to-absorptance ratios to those in the cavity with higher ratios, leading to a perpetual increase in energy concentration and contravening the second law of thermodynamics. This elegant argument hinged on the concept of a blackbody, an idealized object that appears black because it absorbs all incident radiation, and is therefore, in equilibrium, a perfect emitter of radiation across all wavelengths. The concept of the blackbody would continue to prove central in the study of thermodynamics and quantum mechanics. The mechanism underlying Kirchhoff's law is rooted in the fundamental interactions between matter and electromagnetic radiation. Atoms and molecules, when heated, possess greater kinetic energy, leading to oscillations. These accelerated charges radiate electromagnetic waves, which is what we perceive as light and heat. But if an object is placed in an environment where light is present, that light can interact with atoms and molecules, and the energy of the light can be absorbed, again exciting the internal structure of matter. A good absorber is, equally, a good emitter at the same wavelength. The initial applications of Kirchhoff's work were immediately apparent, particularly in the realm of astrophysics. The analysis of the spectra of stars and nebulae was transformed. Prior to Kirchhoff's work, astronomers had struggled to interpret the complex patterns of dark and bright lines observed in stellar spectra. Kirchhoff's law provided the crucial link between emission and absorption, allowing for the direct identification of the chemical elements present within the atmospheres of stars. Bright emission lines, for example, were now recognized as characteristic of hot, rarefied gases. Dark absorption lines, conversely, indicated the presence of cooler gases intervening between the hot source and the observer. This understanding laid the foundation for the burgeoning field of stellar spectroscopy, enabling astronomers to deduce the composition, temperature, and even the motion of celestial objects. The impact of Kirchhoff's work extended beyond its immediate applications. It stimulated further research into the fundamental nature of light itself. It played a crucial role in driving physicists toward the understanding of the links between electromagnetic radiation and the internal structure of matter. The law provided an essential framework for understanding the distribution of energy across different wavelengths, a problem that would eventually lead to the development of quantum mechanics. The reception of Kirchhoff's work at the time was largely positive. Scientific collaborators and contemporaries swiftly recognized the power and elegance of the analysis, though not without initial debate. The fundamental principle ultimately gained wide acceptance due to its ability to explain a range of experimental observations. It was a triumph of theoretical physics, grounded firmly in experimental verification. The principle also found application in areas beyond astrophysics, including the study of heat transfer and the design of thermal devices. It provided a theoretical foundation for understanding the behavior of radiation at different temperatures and for designing efficient systems for heat absorption and emission. Kirchhoff's work also provided significant impetus for further theoretical investigations. One of the most important directions of research, directly inspired by Kirchhoff's law, was the quest to determine the precise form of the universal function of the emission. This quest, pursued over the following decades by physicists such as Wilhelm Wien, Max Planck and others, would eventually lead to the development of quantum mechanics. Wien proposed a displacement law, describing the shift in the peak wavelength of the emitted radiation with temperature. This was followed by the work of Planck, who formulated a formula that accurately described the spectral distribution of radiation from a blackbody. Planck's derivation, which relied on the revolutionary concept of quantized energy, marked the birth of quantum mechanics and fundamentally reshaped our understanding of the universe. The influence of Kirchhoff's work extended also to the development of new experimental techniques. The understanding of the spectral properties of matter spurred the construction of increasingly sophisticated spectrometers. These instruments allowed for precise measurements of spectral lines, enabling scientists to probe the chemical composition of substances with greater accuracy. The advances in spectroscopy, in turn, fueled progress in other areas of physics, including atomic physics and molecular spectroscopy. Examining specific influences, Gustav Kirchhoff drew significantly from earlier studies on light, heat, and the relationship between them. The works of Joseph Fourier, notably his analytical theory of heat, provided some mathematical tools and concepts that were relevant to understanding heat transfer by radiation. The investigations by John Tyndall on the absorption and emission of radiation by various gases provided important experimental data, but perhaps Kirchhoff's most direct influence was his close collaboration with Robert Bunsen, whose experimental techniques and insights into spectroscopy were critical to the realization of Kirchhoff's theoretical framework. The influence of Kirchhoff's work on others was profound and far-reaching. Bunsen, of course, immediately benefited from his colleagues' theoretical insights. It significantly accelerated the development of spectroscopy as a tool for chemical analysis. William Huggins, the English astronomer, used Kirchhoff's principles to analyze the spectra of nebulae, confirming the existence of elements not known previously, and establishing the spectroscopic methods used to study the composition of stars. Max Planck was deeply influenced by Kirchhoff's work, especially in the pursuit to derive the exact form of the blackbody radiation spectrum. Planck's attempts to solve this problem, guided by Kirchhoff's insights, eventually led Planck to his groundbreaking quantum hypothesis. The concept of the blackbody, itself a consequence of Kirchhoff's theoretical work, was central to this achievement. Albert Einstein, in his work on the photoelectric effect, drew directly on the foundations laid by Planck and therefore, by Kirchhoff's law, therefore, is more than a mere equation. It is a landmark contribution to our understanding of the physical world. It clarified core principles surrounding the interplay of energy, matter, and radiation. It fundamentally shaped the development of modern physics, laying the foundation for quantum mechanics, and it revolutionized astronomy. As an example, it provides a tangible example of the power of theoretical physics to explain and even predict phenomena. This work demonstrates the importance of connecting theory and experiment, and exemplifies the profound impact that a single, elegant idea can have on the development of science. The legacy of Gustav Kirchhoff's work on heat radiation is one of enduring significance, solidifying his place among the intellectual giants who have shaped our comprehension of the universe. It serves as a permanent reminder of the interconnectedness of scientific disciplines and the capacity of human intellect to comprehend the complexities of the natural world.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.